So I'll be talking about our work, Constraints on Compact Dark Matter from Gravitational-Wave Microlensing. This work is done with the collaboration with all these people mentioned here. And for your reference, this is the publication of our work. So, okay. So in the introduction, we know almost 25% of the mass energy content of the universe is filled with some unknown form of matter, which interacts only via gravity, and this form of matter is known as dark matter. So if a significant fraction of this dark matter is in the form of some compact objects, they will cause microlensing effects. I'll talk about this later in the gravitational wave signals, which are potentially observable by LIGO and Virgo. And from the non-observation of microlensing signatures in the binary black hole events from the O1, O2, and O3A runs, we constrain the fraction of compact dark matter, and this fraction we denote as FDM in the mass range 100 to 100,000 solar mass. So people who were not aware of these terms O1, O2, O3A, these refer to the observing runs of LIGO, and here FDM means the fraction of compact dark matter. So if it ranges from 0 to 1, so if FDM is equal to 1, it means all the dark matter is in the form of compact objects, and if it's zeros, then it means there is no dark matter in the form of compact objects. So okay, so let's talk about gravitational lensing. So it's the deflection of electromagnetic or gravitational waves from its path due to the presence of an intermediate potential is called gravitational lensing. Here it's a ray diagram of lensing. In the case of gravitational lensing, you have a source, suppose a binary black hole merger, then it gets deflected due to the presence of the lens. Here it is a galaxy, and here in your detector you see the bent GW, which is gravitational lensed here. Okay, and then lensing. Lensing is broadly divided into two categories. One is the geometric optics limit, where the wavelength of the wave is less than the characteristic size of the lens. Here, the characteristic size is the Schwarzschild radius of the lens. Here, we get to see the constant magnification. That there is no phase shift in this signal, and this is generally true for light. And on the other hand, the lensing in the other case is called the lensing in wave optics limit, where the wavelength is comparable to the Schwarzschild radius of the lens. Here we get to see the frequency dependent magnification, and since for the case of GWs, its wavelength is much longer than light, so it can happen for the case of GWs or gravitational waves, and this is our main focus in our work. And this phenomenon, the lensing in wave optics limit, is loosely called as microlensing of GWs. I'll be using this term microlensing next onwards. Okay, so the microlensing of GWs by point mass lens. Okay, so we are considering the lenses to be point mass lens here. So for the case of point mass lens, we have when the GW is magnified in the presence of the lens, we have this frequency dependent magnification term, and HUF refers to the unlensed waveform and HLF refers to the lensed waveform. And in the left column, we show the lensed as well as unlensed waveform in different for different lens mass combinations, and this is the frequency domain waveform. Here, the MLZ term refers to the lens mass, actually redshifted lens mass, and Y is called the dimensionless source position. You can think of it like you have your observer is here, your lens is here, and from this line, how far away is your source? That quantity is defined by this Y term. It is a dimensionless quantity. So I have shown here for two cases, 100 solar mass and 1000 solar mass. And this gray line refers to the unlensed waveform, and similarly, the right panel or column shows you the waveform, GW waveforms in time domain. Okay, so how do you say GW is lensed or not? So to quantify this, we model a statistic. We call it as odds ratio. So this is defined as the where we define two hypotheses. The signal is lensed and the other signal is unlensed. And the odds ratio is defined in terms of these two quantities. This is called a posterior probability distribution. The definition is posterior of HL, that is the signal is lensed given the data over the other one, that is your signal is unlensed given the data. And this can further be divided into two quantities. The first one is independent of your data. That's why it is called your prior odds. And the other one is something called base factor. So when you have your signal, you do your Bayesian model selection, and if your signal is truly lensed, then you have to have this number OLU, or your odds ratio should be much greater than 1. Or in terms of, if you call it as in terms of base factor, it should be much greater than 1. Okay, so in this plot, I am showing you, don't get scared by looking at this plot. So this plot, the horizontal axis, lower axis, shows you all the GW events which are detected in O1 and O2 observing grounds. And let's particularly focus on this first event, GW 150914. And the upper one, upper horizontal axis show you the values of your base factor values in log scale. And also the y-axis shows you the posterior of your lens mass, actually the log lens mass in solar mass units. So if we focus on the first event, so it shows it doesn't show any kind of sharp peak in your posterior. And also if you look at that shows that this is kind of a signature that it is not lensed. If you look at all the other posteriors, those are also broad. And also, if you look at your statistic values, the maximum that is observed in your O1 and O2 events, in terms of log 10, it's 0.2, and in terms of ln base, it's 0.5. So these values are quite small to support your lensing hypothesis. Okay, so this is all about your O1 and O2. And if we include the extra events, so far in O1 and O2, we have 18 events that I showed you in the last slide. And if you include 36 extra events from your next observing ground, which is the O3A, you have total number of events 54. So in the analysis of O3A, the maximum observed base factor is 1.15 in alien base. And and this plot shows you the cumulative histogram or distribution of your observed base factor values in your actual GW data. And you see the maximum of base factor is 1.54 among all these 54 events. So this shows you that there is no compelling evidence of microlensing signature in your observed GWs. Okay. So how do you compute or calculate the posterior on the fraction of lensed events? So we are given the data that we have total 54 number of events, GW events, and we have observed no lensed events so far. And we can compute the posterior on their. So NL equal to 0 means doesn't directly imply that your compact dark matter is 0. So what do we do here instead? We assume that it follows some Poisson distribution with a mean for the case of total number of events as lambda, and for the lensed case, it has a mean of lambda L. And this allows us to compute the posterior on the lensing fraction, which is defined as lambda L over lambda, and denoted by this by EU. And the first column, the first plot shows you the posterior distribution on lambda, which is the Poisson mean for the total events. The middle plot shows you the posterior distribution of the mean of the lensed events, and the third one shows you the fraction of the posterior distribution of the fraction of lensed events for given the data that we have observed 54 of total events, and none of them is lensed. And the different plots correspond to different prior choices. The solid one corresponds to the flat, and the dashed one corresponds to Jeffreys prior. Okay. Okay, I was trying to avoid much.
You have 5 more minutes.
Yeah, I'm in the 9 slides. Thanks. So how do you relate the dark matter fraction with lensing fraction now? So we have calculated our lensing fraction. Now we want to find a dark matter fraction given by computing this data, after computing this data. So for this, we do what you call astrophysical simulation, and we simulate a population of binary black holes and compute the fraction of detected lensed events. So what it mean by lensed events here? So the observed maximum log base factor is 1.15. So we from our simulation, the events which cross this threshold value, we call them as lensed event, and from there we mm, yeah, so we calculate in terms of this log base factor value, we calculate the lensed events and in the LIGO network for different values of FDM. And here also we assume that masses are distributed uniformly in comoving volume. And this is the equation that we can use to compute the fraction of dark matter, where we have once we calculate this, the fraction, the lens fraction. From here, we want to translate to the fraction of compact dark matter, and this factor is called the Jacobian, where you go from U to FDM. With the given data that you have observed NL equal to 0, lensed event equal to 0, and the total number of events equal to 54. Okay, so this plot shows you the lensing fraction for different values of FDM, and the three corresponding plots correspond to different choices of your source redshift distribution, and different this is done for four choices of your lens masses, starting from 100 to 100,000 solar mass, and the line style all the different line style corresponds to all your different choices of your PhD, O1, O2, and O3A. Okay, so then this plot shows you, once you have calculated your Jacobian and also the posterior on your lensed events ratio, then you can translate this to calculate the posterior on FDM. So this plot shows you the posterior on FDM given the data NL and N, and this is done for 100 to 100,000 solar mass lensed events. And the solid line corresponds to the choice of your flat prior, and the dotted lines correspond to the choice of your Jeffreys prior. And again, similarly, the three plots refer to different choices of your source redshift distributions. And here this dotted circles, the circles correspond to your 90% 90% upper limit of your FDM. That is, you have your FDM distribution here for all the choices of, sorry, you have a posterior distribution of FDM, and you put a 90% upper limit for each lens mass cases. Once from there, you calculate the upper limit of your FDM with 90, and this is called your 90% confidence with 90% confidence interval level. Okay, so this is the final plot. This shows you this is called the exclusion plot, and this shows you the upper limits on FDM with 90% confidence interval. And so how do you read this plot? So this region means that this region is excluded. That is, the maximum or the upper limit of FDM for the corresponding lens masses can be anywhere between 0.5 to 0.8 if we combine these two plots, depending on the choices of your prior as well as your source redshift.
You have 1 more minute.
Yeah, I'm done almost. And these dotted lines correspond to some existing priors, existing constraints from your electromagnetic observation. So this shows that our constraint is modest, but this can be improved in future. So this is the expected FDM upper limits from future detection. So far we are here. We have used n equal to 54 number of events till O3A, and we see that the upper limit is it's like we say it modest, like it's not so good. It's close to 1, but it can be significantly improved in future when we have of the order of 1,000 number of events. And this is how this simulation is done assuming a lens of 1,000 solar mass, and this is how it goes. Okay, so in summary, sorry. And non-observation of microlensing signature in GWs helps us put upper bound on FDM. And the limits depend on the assumed redshift distribution of BBHs as well as the Bayesian priors used in the analysis. Nevertheless, we are able to put upper bounds on FDM from 0.5 to 0.8. It depends on the choices of various things. And these bounds will get significantly better in the next few years with the increased number of events and an increased lensing optical depth. I haven't defined this before, but okay, let's skip this for this timing. In our ongoing work, which is also part of the LIGO-Virgo collaboration, is on obtaining the improved constraints using the OCB data. That is, we are currently here now. This is the ongoing work. And yeah, thank you.
Thank you, Soummyadip. We can have only one quick question due to the time bound.
Hello. Yeah, so during the construction of the posterior on the MLZ, so what the distributions on OI, or what is the maximum value of OI you have considered?
Oh, so you can choose a large value of OI so that your detectable events, all your detectable events lie inside that Y. So it depends on your choice of maximum base factor. Suppose you choose your maximum Y, so let's call it Y naught. It should be technically, theoretically can be infinity, but that means all your events are lensed. But in reality, all your events are not lensed. So you choose some finite Y. Suppose you call 5 or 6, something like that. So in such a way that all your detectable events lie inside that Y, and you do not miss your detectable events in that way.
Okay.
Yeah, thank you.